Have you ever wondered how a link shortener works? Are you simply tired of building the 90th to-do app in a row? Or are you still looking for a project to build in Rust? Whatever it is that brings you here, we are going to build our very own link shortener in Rust. A link shortener that also tracks link engagement and teaches you a little about async Rust with Tokio, Axum as a web server, and using databases with our favorite language. The goal is to create a foundation for a production-ready service that you could, in theory, deploy right away. So not only tutorial code, but also metrics and tracing built in, as well as some safety measures so you don't end up with a production outage right after finishing this tutorial. Ready to go? Awesome. But let's first take a look at how such a link shortener could look before we jump into code. In its most basic form, a link shortener is nothing else than a web server that takes a GET request to a specific URL by a browser, extracts some form of ID from the path of the request URL, uses that ID to make a lookup in a database to find the target URL, collects some metrics and statistics, and redirects the browser to that target URL if it exists. That's basically the core logic of any link shortener or link engagement tool that exists. Nothing more. If you want to implement such a link shortener, you mainly need one API endpoint that takes requests and returns a redirect, an endpoint that allows you to create new short links, an endpoint to modify an existing short link, which is especially useful for marketing campaigns and A/B tests, and you will also need an endpoint to access the metrics and statistics you collect about each link click, which brings us to a total of 4 API endpoints to implement. That's pretty doable. The only thing left to think about for now, before we finally dive into code, is how do we effectively shorten our links? In the end, we want to take any URL and create some form of ID from it. If a user then clicks on the resulting link, we want to redirect them to the actual URL. But this raises the same problem that other link shorteners face with their IDs. If they are easy to guess, anyone can basically try to iterate over all IDs and see where they land. Not all customers might be happy if someone gets hold of a semi-public page or at least gets to manipulate the engagement statistics of a link you have shortened for a marketing campaign. Deriving a hash from the URL itself might be an option, but it can also lead to collisions. And link shorteners usually don't care about whether you create more than one shortened link for the same target URL. So we can rule that out. But what then? Well, a relatively easy way to generate a unique ID, which is not that easy to guess, is to use a relatively safe random number generator and then encode the result with base 64. Generating a random number as an unsigned 32-bit integer, for example, already gives you a lot of available IDs. If you pair this with some form of rate limiting, it will take an attacker a considerable amount of time to try out every possible shortened URL. And if you additionally have a web application firewall in place, the attacker's IP will probably get blocked faster than they can try to get a new IP and continue their attack. So that's a fast and effective way to generate unique IDs for shortened links. Now that we have set the foundations, let's finally jump into code. Let's first create a new folder and call it link shortener for now. Next, change your directory into that folder and then initialize a new Rust project with cargo init --bin, which will spin up a super simple binary application project for us. Let's now open our IDEs and install our very first dependencies. What we need for now is Tokio as our asynchronous runtime, Axum as our web server, and tracing as well as tracing subscriber to log messages later. We want Tokio with the full feature set, and tracing subscriber with the env filter feature, which brings us to a total of 4 dependencies to get our link shortener up and running. Let's now modify our main function to actually make use of Tokio. The first thing we want to do is to add the Tokio main macro right above the function, so we can make the whole function async and use await within its body. Then, we change the return type of the function to result of unit and box_dyn error, which allows us to make use of the question mark operator to bubble up errors we don't want to handle. After that, we let the function return OK unit. The next thing we want to do is to create a new file called routes.rs that will contain all of our API's endpoints. Now that we have a place for all our endpoints, we can begin to implement the basic first endpoint for health checks. It's a simple async function that takes no arguments and returns impl into response, which allows us to return anything that Axum can internally convert into a response. In our case, that is a tuple containing an HTTP status code and a simple message. A dedicated health endpoint is usually helpful if you want to deploy your software to Kubernetes or other platforms that regularly check whether your application is still up and running. If your IDE, like mine, doesn't automatically add your new module to the main.rs, make sure to add it there. Otherwise, you won't be able to integrate that new endpoint now. What we now want to do is to initialize our tracing, which also handles logging through the tracing subscriber crate. It allows us to set up the behavior of the tracing crate with composable layers, which is also easily extendable. Each call to with adds a new configuration layer. In this case, we begin with an AND filter that reads tracing configuration from the environment variables. We also supply a fallback to at least log all messages specifically belonging to our artifact at the debug level. In this case, we especially want this filter to enable reading of the Rust log environment variable. The next layer we add is the format layer that logs formatted tracing events to stdout. After that, we can initialize the tracing setup and perform the required imports, which are subscriber init ext for init and subscriber ext for the layered with API. With our logging set up, we can now integrate our health endpoint. A router is Axum's API for HTTP routing. With a call to route, which takes a path as its first argument, and a handler, get in this case because we want to respond to only GET requests, as the second argument, we can integrate our health endpoint. The next thing we need to set up Axum is a TCP listener, which accepts traffic and forwards it to the actual HTTP layer. As Axum builds on Tokyo, we need a Tokyo Net TCP listener that we bind to all network interfaces on port 3000 in this case. That's an asynchronous operation, so we need to await the call and get a result in return. If the TCP listener can't be initialized, we can't start the server, so we can safely expect the result and let eventual errors crash the whole service because it would otherwise be in an unrecoverable state. At this point, it makes sense to use the tracing crate to print out a debug log stating which address the TCP listener was bound to. Although the address is currently hard-coded, we might want to make it configurable at some point, or we might simply forget which address we used. For this to happen, we need to retrieve the local address of the listener and expect it once again. This call should usually not fail. If the listener could be set up correctly, it should also have a valid local address. And now, we can finally start our Axum web server by using Axum serve, which receives the listener as its first and the router as its second argument. We are once again dealing with an async API, so we need to await the call and get a result in return. As before, we can simply expect the result. If the call fails for any reason, we get at least an error message that helps us out a little. We have, however, not yet fully finished setting up our service. Observability is an important topic, and one way to monitor our service is through metrics. In the world of containers and Kubernetes, the most prominent metric stack builds upon Prometheus. So let's put in a few more dependencies. We want the metrics crate, which gives us ready-to-use macros to record metrics, metrics exporter Prometheus, which makes these metrics available to Prometheus, Axum Prometheus, which comes with pre-made metrics for Axum services, and Tower as well as Tower HTTP with the trace feature, which also add a little default logging. These crates make it way easier for us to focus on our actual logic because we don't have to deal with too much logging. And the metrics crate allows us to create metrics anytime without much further setup. After installing these crates, we can now go back into our main.rs and work on integrating them. The first thing we now need to do is to add the Prometheus integration. We do this by initializing a Prometheus metric layer, which returns a tuple. The first member of that tuple is a tower layer that collects some default metrics from our Axum service. And the second one is a handle that we can use to expose all collected metrics through an HTTP endpoint that Prometheus can later scrape. Speaking of the endpoint, we can integrate that by adding a new route to our router with the path metrics and a handle function that is triggered for GET requests. Unlike our health route, however, we need to pass an async closure, which calls the render method of the metric handle. After that, we can work on integrating our layers into the router. The first layer we add is the trace layer, which uses the same tracing lib that we have previously integrated to record a few tracing events whenever any of our endpoints is called. Then we can integrate the layer that the Prometheus metric layer returned as the first member of the tuple. This gives us a pretty robust basic setup that allows us to iterate on. We now have tracing and metrics and already record a few very essential events. Time to start our new service for the first time and see whether everything works correctly now. For a very basic test, it's enough to just open our browsers and see whether we can reach our service locally. A good first target is the health endpoint that should now return a successful response and the string that we should see within our browser. And if we go to the metrics endpoint afterward, we should already be greeted by our first recorded metrics. With a running service, we can now get into setting up our persistence. So let's add a few more dependencies, beginning with sqlx with the features runtime Tokyo rustls and Postgres, because we are going to use Postgres as our database. Next, we add .env, which is a crate that allows us to use .env files. sqlx, by the way, is a crate to interact with databases. It even compile time checks queries and comes with some object mapping capabilities, which relieves us from having to use a fully-fledged ORM. SqlX also has a CLI that comes with support for managing databases and especially migrations. If we work with SqlX in this project, it makes a lot of sense to install it. The crate usually has support for many more databases, but for now we only need support for Postgres, so it makes sense to also only install it with these features, especially because the CLI also has native dependencies for databases you probably don't even work with. Now that we have the CLI, we need a database, because our queries are checked against a real database at compile time. Let's use Docker Compose for this purpose and create a new Docker Compose YAML. Feel free to copy the YAML as shown here, but you're also free to use any Postgres instance you might have available elsewhere. If you decide to go with Docker Compose, it's now time to start our database with Docker Compose up-d, so the database runs in the background. With our database running, we can now create a .env file to store our database URL in. The SqlX CLI can also read the .env file and make use of it, which makes our lives a little easier. In this case, we just drop the URL to our local database within the .env file. After that, we can use the SqlX CLI to create our database and then create our first migration. By adding the R flag to the command for creating a migration, SqlX creates a revertible migration with scripts for both migrating and reverting a change. This makes it easier to roll back the database in case we screw up or simply need to go back. Let's now fill our first database migration with live and create a table to store our links in. What we need are two columns, one ID column, which is the shortened link ID, and a target URL, which is the target our shortened link points to. We do of course also need a way back, because we went with revertible migrations, so we also need to make sure to fill the down script, such that we can undo the migration we've just added. In this case, all we need is to drop the table when reverting, which automatically also deletes all data it contains. Let's now get back into our main.rs and implement the database initialization. The first thing we need to do is to initialize .env and make it read our .env file. Then we can read the database URL we have previously put into our .env file from the environment variables. Reading environment variables does not always yield a result, which is why std-env var returns an option. In our case, we need that value to continue our work, so it's fine to expect it and let the service crash if it isn't available. Letting the container crash is also a nice indicator if we decide to run the service in a container environment. If we forget to provide the database URL, we don't start in an undefined state. With our database URL available, we can now create a connection pool, which in our case can hold 20 connections to use. And PG pool options from SqlX provides all the configuration we need for that. Additionally, the API directly tests whether it can connect to the database, which saves us from experiencing connection errors at runtime, which could have been caught on startup. And now we can take that Postgres connection pool and provide it as state to Axum. A call to with state registers the pool, which is already thread safe by the way, as global state to our app, such that we can use it in any of our handlers if we wish to. Before we can continue, there are two more dependencies we want to pull in now. Our API is going to work with JSON, so we need a library to handle that for us. This is why we now want to install CRD with the derive feature and CRD JSON, so we can easily serialize and deserialize some structs. With JSON support at our hands, we can now create a utility method we will need a few times to handle most errors for us. Let's create a new Rust file and call it utils.rs. And now we create a new function within that file that will be our generic error mapper. What we need is a simple function that takes a generic error and returns a tuple containing a status code and a string, which will be what we return from our API if any operation fails. We can define the bounds of our generic parameter with a where clause that states that we only accept errors from std-err. That's a little more readable than placing the bound right inside the prototype of the function. Inside our bodies function, we first want to log the error through the tracing crate. Doing it in the central place will hopefully save us if we forget it in other places. We also still have metrics available, so let's first create a few labels we can attach to our error metric. These labels are just an array containing a tuple, which in return contains a key and a dynamic value, our error in this case. With these labels, we can now increment a counter that keeps track of the number of errors an instance of our service has experienced. Thanks to the metrics crate's macros, that's pretty easy. We just need to give the counter a name and pass the labels, and the macro does the heavy lifting for us, so we don't need to take care of metrics instantiation and such. With that done, we can let the function return a tuple containing an HTTP 500 for an internal error, and the stringified version of the error message. If we later use that function as an error mapper, we can quickly turn errors into valid responses without manually having to take care of that each time. Okay, I know. We've been doing quite a lot of setup until here. So let's finally get into implementing our actual link shortener. Back to our routes module to finally implement our redirect endpoint. We now want another handler that is an async function which takes our database connection pool as state of type state pg pool as its first argument, and then we do, of course, also need a reference to the ID of the link that was requested, which will be our path parameter as the second argument. As it is a path parameter, we can safely let Axum pass us a string, which then contains the ID of the requested link. Our redirect handler should return a result that either contains an Axum response or, in the error case, a tuple with a status code and a stringified error message in it. Before we can write our first query, however, we need an object to hold the data we pull from the database in. So let's create a struct that does exactly that. We will call it link and give it the same properties that the link table in our database has, which is an ID with type string and the target URL also of type string. Oh, and if we are on it already, let's quickly add the derive macro to allow COD to deserialize as well as serialize our link struct from and to JSON. Additionally, we also need to tell COD to rename the JSON properties to camel-cased ones. Otherwise, we end up with snake case names, which is not that great for less civilized languages out there. Awesome. Let's finally implement our first database query inside the redirect function. When the redirect handler is triggered, we first want to try to fetch the corresponding link from the database. We can do that by using query as from sqlx, which accepts a struct as its first and a query as its second argument. Thanks to it being a macro, we can place any variables we want to bind to the query after that. The struct, link in this case, tells sqlx to extract the resulting columns from our query and put them into the corresponding properties of the struct. The query is, well, just the SQL query we want to execute. And the third argument in this case is the requested link, which sqlx automatically sanitizes and places inside the query. After that, we need to tell sqlx what exactly to do with our query. In this case, we want to fetch an optional result, because the link we try to find inside our database might just not be present with the ID we got. Then we can await the result in future and finally make use of our utility error mapper. For now, it's enough to just map all errors that might potentially arise from this sqlx call to an HTTP 500. As both our utility error mapper and our handler return a tuple of status code and string in the error case, we can make use of the question mark operator, which will immediately return our mapped error if something went wrong. This also unpacks the result, which leaves us with an option. But we can convert that option back to a result by using OK or else, which turns a sum into an OK and a none into an error containing the provided default as error. And as we now have a result again, we can use map error to turn that default error message into a tuple response containing an HTTP 404 and our error message. With the question mark operator applied to this map error, we create another early return. Let's just quickly reformat this code before we continue, so everything has its correct indentation. With our first query done, we can use the opportunity to create a debug log statement that simply logs for which link ID we redirect users where to. Mistakes happen, and in the future it might be nice to be able to quickly redeploy the service with debug logging turned on to identify bugs. What our function is missing, however, is a return statement. So let's implement that. Axum has a response builder we can use to create a custom response with all properties we want. In this case, that is an HTTP 307, which is a temporary redirect. We want a temporary and not a permanent redirect because browsers might otherwise decide to cache this response forever. This will prevent us from ever changing the target link, which is not what we want. The next thing we need to return is a location header, which instructs clients where we actually redirect them to. The value of the header is, of course, the target link we have previously fetched from the database. After that, we attach an empty body, because there's nothing else for us to return. Then we expect the result from the call to body, which should usually not result in a panic unless we create a bug by accident, but in this case, that's exactly what we want. Although we use a temporary redirect to prevent permanent caching by browsers, we can still profit off caching ourselves. If a post really succeeds on social media, for example, we might get many visitors, and some of them might even click on a link multiple times. This creates a lot of traffic, which we can save our service from by issuing a caching directive ourselves. We won't do that inline, however, because it's going to be a pretty large cache control value. So let's create a constant for that we can place at the top of the file. This makes it easier to find it again later, just in case we ever want to change the corresponding values. What we place inside that constant is the value for the cache control directive. In our case, we want to allow any caching layer between our service and our users to cache our response, which makes it public. Next to that, we allow browsers to cache the response for 5 minutes, which is what maxh does, and additionally allow caching layers to also cache it for 5 minutes, which is what smaxh is for. Another trick we can pull up our sleeves is stale while revalidate, which allows browsers and caching layers like CDNs to reuse a stale response while fetching a fresh one in the background. This speeds things up a little. We can also allow all parties to reuse the stale response if our service returns a non-successful status code, which increases resiliency. This is what stale if error is for. As we have our constant now, we can go back to our return statement from the redirect handler and add a cache control header to the response, so we can instruct browsers and caching layers to act accordingly. Thanks to our constant, we can easily drop it as a value for the header and adjust things at the top of our routes file, should the need ever arise. There's one thing, however, we can still do to improve the resiliency of our redirect handler. Right now, we will wait forever if our database ever becomes slow or unresponsive for some reason. That's not ideal. It's also never great to show users an error, but doing so earlier is better for UX than later. Thankfully, we already have the right tools at our hand to implement a timeout, so we don't wait for calls to our database to return forever. Tokio already comes with APIs for timeouts, so let's make use of them. First, we need a duration from Tokio time, which defines for how long we are willing to wait until an asynchronous call should be cancelled. In our case, 300 milliseconds should be more than enough time, even for a database under pressure, to respond to a query. Second, we need to wrap our sqlx query into a timeout. We can do that by calling Tokio time timeout and pass the duration as its first argument and our sqlx query as the second argument. This wraps the whole result from the call to sqlx query as in another result, which contains a timeout error if we run into one. And this means that we need to unpack another result in our call chain, which we can do with map error once again, using our utility error mapper and the question mark operator to return early. Great! Let's quickly reformat our code again to give it the right indentation, and then once again appreciate how far we've come. But before we forget what we are here for, let's first register this handler with our service, so it can actually get triggered by a request. Back to our main.rs and off to the declaration of the Axum router, where we create a new route which points to /:id. This route should accept only GET requests and handle them with the redirect handler we have just finished implementing. Great, now we can technically redirect requests, but we don't have any way to create a shortened link yet, so it's about time we create a way to do exactly that. Let's go back to our routes.rs to create a handler for creating short links. But as we build somewhat of a RESTful API, we first need another struct, which models the body of the post request we will accept. For the sake of this video, let's call it link target and give it just one property, the target URL we want to save to later redirect to. We only need the single property because we will generate the ID ourselves. This time, it's enough to just derive cd deserialize for our struct because we don't plan on returning it from one of our handlers in any way. And like we already did for link before, we also make sure to automatically rename our property to camel case to keep it consistent. Good. Time to implement our next handler. So let's create a new async function and name it createLink. Like with redirect before, it receives our database pool as type state pgpool as its first argument, and this time the link target struct in JSON form as its second argument. Axum gladly already has an extractor for that, so we don't need to pull it from Axum's request ourselves. Our handler function should once again return a result, but this time it either contains a JSON representation of a link, or, once again, in the error case, a tuple of status code and string. Before we start to flesh out the body of our function, however, we need another dependency. It would be foolish of us to accept anything as a target URL, so let's verify that we really get one by leveraging the URL crate. With that crate installed, we can, as our first action, extract the target URL from the JSON body our handler receives. Then we can try to parse it. If that fails, we know that we haven't got a valid URL and can reject the call. A good way to do that is to use map error once again. This time, however, we return an HTTP 409 and early return with the question mark operator once again. After that, we stringify the URL again, which ensures that everything is correctly encoded and we can safely store that URL within our database and redirect browsers to that location later. Before we continue, let's quickly install another two dependencies. We need the rand crate to generate unique numbers and the base64 crate to then encode these numbers into strings. And with these crates installed, we can create a new utility function that will handle the generation of shortened link IDs for us. Let's call it generate ID and let it return a string. The first thing we need is a random number, which we can generate with the rand crate. We can do it by using thread_rng with a range, which limits the possible results. In our case, we want anything between 0 and the maximum possible 32-bit unsigned integer. Now we want to encode that random number with base64, and we can do that with the general purpose engine from the base64 crate. More specifically, it's URL safe notepad engine, which ensures that we keep a valid shortened URL. Great, let's use that utility function within our handler now, so we can generate a new ID for a new shortened link. We want a new variable, we'll simply call it new link ID, and assign the result of calling our generate ID function to it. Then we want to create a timeout duration because using a timeout to save a new shortened link makes as much sense as using one when fetching it. So let's create a new Tokyo time duration, also with 300 milliseconds. Once again, having a timeout does not particularly protect our database, but it protects our users from waiting too long. And that is also pretty good already. We can now use that timeout, like before when we implemented our redirect handler, to create a Tokyo timeout wrapper around our next database query. As its first argument, we pass our insert link timeout to it. And the second argument is going to be our sqlx query. We want to persist a new link, but also directly get the persisted entity back so we can return it as JSON to the client. And for this, we pass the link struct as the first argument to query s, and then create our SQL query. In this case, we will use a with clause, which allows us to create a temporary relation. And within that temporary relation, we can place the insert statement to persist our new shortened link in. As our link entity only has 2 columns, that's done pretty fast. We only need the ID, which we previously generated, and the target URL that we've already verified to be a valid URL. We can then close the with statement by returning exactly the 2 columns we have previously inserted. This now allows us to add a select statement, where we can select again what we have previously inserted. And this, in return, allows us to return exactly to any client what's in the database, and not what we assume to be. Now we need to bind the variables that we have previously only numbered with $signs. So let's add our generated ID as the first, and the verified target URL as the second bound variable. As we know that we only expect exactly one result, we can use fetch1 to tell sqlx that we want exactly one definitely existing result. After that, we need to await the async call and then add our map error chain again to ensure that we return early if anything goes wrong and get a filled link struct in the end that we can continue to work with. Okay, let's quickly reformat that before we continue. Great. And now we should add another debug trace to ensure that we have at least something to look for if we should ever need it at some point. Stating the ID of the created short link as well as the target URL it points to should be enough for this statement. That's all we save in our database anyway. And for the rest, we still have the tracing layer that gives us a little more context about the call. The last thing here is to now return the JSON representation of the link we've just created to inform our caller about their newly shortened link, and especially to give them the ID they now need to use. Awesome. Time to integrate our new handler into Axum. So let's jump back into our main.rs and add a new route to the router. We can't go down a completely RESTful route because, well, we create the ID, and we don't want the client to say which ID a short link should have, which is why we choose the path create for this handler, and then define that we only accept post requests for this particular path. We should probably take our link shortener for a test right now. So let's start our service and then open a terminal, so we can use curl to send the post request to test whether creating a new link really works. If we now post to the create endpoint, we should see a successful response, including a JSON string, which contains the generated ID, as well as the target URL that was saved within the database. And if we now issue a GET request to the path under the ID we've just got from creating a new short link, we should see a temporary redirect and the location header pointing to our chosen target URL. We can test the same with our browser, so let's open a tab and try to access the same URL we've just requested with curl. And as you should now see, your browser should have ended up exactly at your target URL, which in my case is my own website. Well, this means that what we have done so far worked out, which is awesome. Let's appreciate that again for a moment and then get back to work because we are not done yet. The next thing we want to add is an endpoint to modify short links. Sometimes if a post on social media does good, for example, we might want to test another variant of a landing page or something like that. And in this case, it might be beneficial to be able to redirect people to another target. For that to work, however, we need to modify the entity within our database. So let's work on that next. Let's stop our link shortener and then go into our routes.rs to work on a new handler that allows the modification of existing short links. We once again need an async function that we call updateLink this time. As before, the handler receives the state with the Postgres connection pool as its first argument. And as its second argument, it receives the path to a short link ID, so we can perform the database lookup based on exactly that. As its third argument, we want to accept the link target in JSON form, which is the same struct we have already accepted when creating a new short link. We once again only need a target URL to replace the old one, so we can reuse what we already have. Our handler should once again return a result, and in this case, we can use the same return type that we have already used for the create handler. A result of a link as JSON, or a tuple with a status code and a string. And with that done, we can continue to implement logic that has already proven itself. Like we already did for the create handler, we should first test that the new target URL is indeed a URL by parsing it. If that fails, as you already know, we don't have a valid URL. And in this case, we can let the whole call fail by returning an error like we did before. This is the same logic we have already implemented for the create handler. If we get an invalid URL, we return an HTTP 409 conflict by mapping the error, and then early returning with the question mark operator. After that, we stringify the parsed URL again to continue work with it. After that, we need another timeout duration because, as usual, timing out earlier is better than never. So let's create one with 300 milliseconds again, such that we can use Tokyo's timeout for our next query. Good. Let's start to implement that query. What we want to do is, once again, wrap our sqlx query inside the Tokyo timeout, which ensures that we never wait too long. Our first argument is the timeout we've just defined, and our second argument is an sqlx query s, which receives the link struct as its first, and the actual query as its second argument. As you might have already guessed from the structure of the function prototype, we once again want to return a JSON representation of what we have saved within the database, so we can leverage a with statement once again to create a temporary relation in which we update a shortened link if it exists. We can return the two columns from the with statement again, which allows us to reselect them in the next step. And like for the create query, we can implement a select statement which directly fetches its data from the temporary relation created by the with statement. Then we need to pass the parsed URL as the first and the link ID as the second bound variable to query as. To get sqlx to return the correct type, we use fetch1, which expects exactly one result or errors otherwise. Now we need to await the whole future and then handle all errors with the map error chain you already know. First we unpack the timeout future and then any database errors while early returning if anything went wrong. Awesome. Let's quickly reformat that small block such that it doesn't hurt our eyes too much, and then work on some more debug logging because you never know when you're gonna need it. So let's use the debug macro from the tracing crate again to create a new trace and log message. In this case, it should be enough to just state that a link with a specific ID is now pointing to a new target. The last thing we need to do is to let our handler return something. In this case, that's the JSON representation of the entity we've just updated within the database. Great. This finishes the implementation of that handler. Time to add it to the router so we can also call it from the outside. We want to attach the handler to the column ID route, and it should be triggered on any patch request. Gladly, Axum has a fluent API to chain method handlers, so we can simply prepend our new handler to the get handler. Okay, let's once again try to test manually whether what we've built so far really works. So time to start our link shortener once again with debug logging enabled, just to be sure, and then open a new terminal. Let's now issue a patch request to modify one of the short links we have already created, which should result in a successful response and a resulting JSON that shows our modified target URL. And if we then jump back into a browser and visit that short link again, we should be redirected to another target this time, which shows that what we've done worked. If you still land on your previous target, your cache is probably still fresh, so use the dev tools to disable it and try again. Until now, we've built a pretty well-working link shortener, but let's extend it a little more and start to track some engagement metrics. These are things like the user agents of people who click on shortened links, and especially the amount of link clicks we got. To kick that off, we need to create a new database migration. So let's do exactly that and call it link statistics. This time, we don't need to pass the R flag to sqlx, as the CLI understands that we already work with revertible migrations by looking at our first migration. And with that new migration created, we can now fill it with live. Let's start with the up script and add a new table to the database, which will hold these statistics we are about to collect. Our table is going to consist of 4 columns for now. An auto-incremented ID column, an ID of the link the particular entry refers to, the referrer, if available, and the user agent, again, if available. The column link ID is, of course, a foreign key pointing to the link table, which ensures that we don't store statistics for links that don't exist. So we need to mark it as such with a foreign key constraint. And lastly, it's a good idea to create an index on our link ID column, because we will usually query data based on link IDs and not on their primary keys. And that index ensures that this access is and stays as fast as possible. As that concludes the up script, we can quickly take care of the down script. So let's switch to it and then ensure that if we revert the migration, we just delete the table, which also deletes all data. And now we can run the migration as we've previously done for our first one, which adds our new table to the database schema and sets us up to do more coding and modify the redirect handler to actually collect the data we want to store inside our newly created relation. The persistence part is now set up, so let's jump back into our routes.rs and navigate back to the redirect handler, where we want to make a few small modifications. The first thing we want to add is a new argument. In this case, that's an Axum header extractor, because we want to be able to access these HTTP headers to extract some information from. One thing we want to extract is the value of the referrer header. The referrer is, if you don't know yet, usually the website which, well, referred to you through link. If someone clicks on a link on a website, the browser then usually sets the value of the referrer header to the URL of that specific website, which in return allows you to see where you get your traffic from. Axum provides a header map, which works like a normal map. To extract the value, we need to call get with a specific key, the header name in this case, and we get an option in return. As the nested value of that option is of type header value, we still need to extract it to a string, which is why we can map the option and stringify the value in a small chain, because we still need to account for possible encoding errors and such. In this case, we don't really care about whether the value was empty or non-existing, which is why we can also live with a default empty string. And the next thing we want to extract is the user agent, which works the same way like the referrer. We only need to pass another key, the name of the user agent header this time, to get, and can then repeat the same code to stringify the value of the header. If dry is giving you PTSD now, don't worry, you can feel free to abstract this small block of repeated logic away if you wish to, but for the sake of this video, it shall be enough to repeat that block one time. As we now have the 2 values of our link engagement statistics we are currently interested in, let's work toward creating our next query. But as usual, we want to use a timeout again, so we need another Tokyo time duration. 300 milliseconds is more than enough for this query as well, so let's lock that in. And then we can work on the query to persist the new statistics entry. As with all other queries before, we want to wrap the actual query in a Tokyo timeout, which receives the duration as its first argument and the query as its second one. This time we'll use a simple query, because we don't want to refresh the persisted statistics, which is why we can use sqlx query in this case, instead of sqlx query as. And because we are using a simple query, we also only want a simple insert statement, and no with statement magic this time. All we do is try to persist a new entry with the link ID, the referrer, and the user agent. This leaves us with 3 variables to bind, but unlike query as, which is a macro, query has no such dynamic argument magic for us, and thus we need to use sqlx's bind API to bind all variables in the numbered order we have placed them inside the query. After that, we can just execute the query, because we are not interested in any results this time. Then we need to await the whole future, as usual, but this time we won't do any error mapping or early returning. Sometimes user experience is more important than correctness. If we cannot persist a new statistic for any reason, we should not let the whole call fail and abort the redirect. Users wouldn't be too happy about that, and we would lose the engagement on whatever we hide behind our short link. What we can do instead is to at least record the outcome of the operation by tracing and logging the different cases. The first case is a timeout, which means that the outer result is an error and contains an elapsed, which Tokyo returns if the database call took longer than we've configured with the duration we passed to the timeout function. In this case, we can only log that we've hit the timeout. The second case is an OK in the outer result, which means that we haven't timed out, but we got an error on the inside, which means that there was some kind of database error when executing our query. There's also not much we can do about it, except logging the issue and providing the sqlx error within the error message to hopefully make sense of when analyzing. The third case is an OK inside an OK, but we can also just use the fallback case for this. This is when everything went well and we have persisted a new statistic for a link click. We actually don't need any logging for that case, but for debugging purposes, it's always a wise decision to include a message which states exactly what we expected to persist. If we somehow end up with a logic error at some point, we can still enable debug logging and see whether our link shortener really did what we expected it to do. This statement could especially come in handy if we ever decide to extend the amount of metrics we collect. The more you do, the more room for error there usually is. Now that we persist some statistics about link clicks, we should also have a way to fetch them. So let's create another endpoint so we don't need to access the database with a DB client and then perform SQL queries to find out how well our links did. But first, we want to create a struct to hold our link statistics in, so we can use query as again to map the data we fetch right onto it. Let's call our struct counted link statistic and give it some properties. Oh, and we will go over why it is called counted in a second. Our first property is amount, which holds an optional unsigned 64-bit integer. That is the amount of clicks we got and also the reason for the name of the struct. The second property is the referrer, which is an optional string. And the third one is the user agent, also an optional string. These two properties are basically the same we are already collecting within the redirect handler. These are all the properties we need for that struct. So let's quickly take care of making it serializable with CD first, and then ensure that we, once again, rename our properties to camel case within the JSON. As usual, that just ensures that whatever client we interact with can actually handle the JSON. Because there's no official rule for that, but camel case somehow became somewhat of a standard. Okay, and now that we have a struct to fill our query data in, we can work on creating a new handler for an endpoint to fetch these statistics with. Let's create another async function and call it getLinkStatistics. This function, once again, receives the database pool as its first argument in the form of a state extractor of type state pgpool. As the second argument, we want a path extractor that gives us access to the ID of the short link we want to fetch the statistics for. The link ID is just a string again. Then our function still needs to return a type. It's once again a result, but this time it either holds a JSON of a vector that can hold multiple counted link statistics, or a tuple of a status code and a string, which is what you are probably used to by now. As our new function now has its skeleton, let's focus on implementing it. We once again want a Tokyo time duration because we will go with yet another timeout wrapper for our query. 300 milliseconds should also suffice for this one. And now we can use another Tokyo timeout to wrap our actual sqlx query in. Like before, we create a Tokyo timeout and then pass our duration as its first argument. The second argument is the actual sqlx query, of course, and this time we will use query as again, because we want to not only fetch data, but also fill our previously generated struct with it. We could now do a simple select to just fetch all entries from the database, but we can also save clients from doing some work. So let's do exactly that and directly aggregate the statistics a specific way. In this case, we want to fetch the statistics by grouping them by their referrer and user agent and their link ID, of course, and then count each group individually. We do of course limit the result to only those statistics that have the matching link ID, which is also the variable we need to bind in that query. As we are not dealing with a single but potentially multiple results, we need to use fetch all this time, which implicitly results in a vec of our map type, counted link statistics. Then we need to await the future and finish with our well-known map error early return chain that first unpacks the timeout result and then the actual query result, which leaves us with the list of entities we can return in the end. But before we return anything, we should add another debug log statement, just in case. We can't add too much of value here, to be honest, but together with the trace logging from the tower trace layer, we do at least get a classical "you are here" log statement. After that, we can return the data we fetched from the database, which hopefully contains useful insights later as JSON, and thus fulfill the request. As our handler is finished, we can once again jump back into our main.rs and work on registering the handler under a path in Axum's router. Let's choose a path under /column_id/statistics, which seems suitable for what the handler does, and then add our handler only under get because it's only fetching data. Great, we've added another endpoint. Time to once again test manually whether what we've built really works. So let's start our link shortener once again, and then access the redirect endpoint with a known short link ID a few times while passing some string as the referrer and some string as the user agent. In my case, that's terminal for the referrer and the user agent of my browser. If we now access our newly created statistics endpoint, we should be greeted with a response similar to what you see here. In this particular case, there are 3 clicks by a referrer terminal and the specific user agent of my personal browser. Incredible. This is all the logic we need to create a well-working link shortener for our personal use. But we haven't paid attention to one very specific thing: security. Right now, everyone who knows at which endpoints which logic resides can create or even manipulate short links. That's probably nothing we want to live with. The solution? Let's add some authentication, so we stay the only ones able to use our link shortener. We need another migration, so let's create one and call it settings. To keep it as simple as possible, we can go with an API key approach. That's basically just a password a client needs to pass in order to access specific endpoints. We can't, however, store such an API key in plain text. It's always a good idea to encrypt such crucial data. So let's open up a browser and use an online tool to encrypt a random string with SHA-3 256 for us. Then we can copy the resulting hash and navigate to the app script from our newly created settings migration. What we want to create is a simple table to hold global configuration or settings in. It gets an ID, so we can uniquely identify a set of settings, and an encrypted API key for now. Additionally, to keep it simple again, we can also directly insert our API key that we have just hashed. Just a quick word of advice, by the way: as you now most probably end up with a secret under version control, make sure to change the API key after you've deployed your link shortener, or otherwise someone might scrape that data at some point and then get hold of your key. With that said, we can quickly fill the down script, which is as unspectacular as the previous ones, because it also just deletes the table if we ever revert that migration. Let's now quickly run that with the sqlx CLI to bring our database up to date. What we now want to create is some Axum middleware to handle the auth part for us. So let's create a new file and call it auth.rs. And by the way, don't forget to register that new module within your main.rs. We will need to execute a query once again, so let's first create a struct to hold the contents of our settings table. We can call it settings and give it the same properties that match the columns of our table, which are a string ID and a string encrypted global API key. To silence any linting which will complain about the unused ID property, we can attach and allow that code to ID and then leave it at this. This time, we won't need any CRD macros, because we neither plan on receiving nor sending them. Okay, this allows us to start implementing our middleware. We just need to create a pretty normal async function. Let's call it auth, because it states exactly what it does. Its first argument is, as usual, a state extractor that gives us access to the Postgres connection pool. Its second argument is an Axum request, which contains all information about the request our link shortener got. Its third argument is a so-called next, which gives us access to the call chain of all layers within our Axum service. This allows us to resume the request later and hand control over to the next middleware or a handler after we finished our work. The return type of our function is once again a result, but this time it returns either an impl into response again, or our beloved tuple of a status code and a string, which is nothing new for us at this point, but does the job perfectly well. Now that our function has a skeleton, let's begin implementing it by creating a labels array for some metrics. For an auth middleware, it makes sense to somehow track for which path called there were how many failed authentication attempts. The counter is going to be the metric itself, but we need a label for the URI, which we can get by accessing the Axum request and fetching the URI associated with it. Then we need to extract the API key from the request. A common pattern is to put API keys in the headers, which is also where other methods like JWT tokens, for example, are usually placed. In this case, we just assume that our API key is placed under the header name x-API-key. We have to transform the header value to a string like we already did in our redirect handler when we extracted the referrer and the user agent. As we have an option at hand, we can transform that into a result with OK or else. If the caller of an authenticated API does not supply an API key at all, we will have a none at hand, which in return will trigger the closure provided to OK or else. And if that happens, we first want to log that we received an unauthorized call. That's a first good warning that something bad might be going on. After that, we can use the increment counter macro from the tracing crate to create and update a metric that shows how many unauthorized calls we got overall. And thanks to the labels that we pass as the second argument, we can then later also group that by the actual URI to see which endpoints bots or malicious actors are most interested in. As the last action inside that closure, we return a tuple with an HTTP 401 unauthorized status code and the simple error message stating that the call was unauthorized. Then we can use the question mark operator once again to early return the result of the OK or else closure if we got no header. The next thing for us is, who would have thought, to create another Tokyo time duration, because we won't stop using timeouts now that we are so close to finishing our link shortener. As usual, 300 milliseconds is more than enough time to perform any query. With that done, we can create another timeout wrapper, which will be around the query to fetch our API key. As before, the first argument to timeout is the duration we've just created. And the second one is an sqlx query ask call again, which in return receives the settings struct as its first argument. The query we execute this time is a simple select, which fetches our default settings from the database to get hold of the saved API key. To make things a little more flexible, we can still use a placeholder variable within the query for the where clause and pass the identifier hard-coded as a bound variable. This makes it a little more visible and doesn't hide it right inside the query. As we expect exactly one result, we can use fetch1 to express exactly that. Then we need to await the future again and append our map early return chain as usual, because we won't be changing our approach so close to our goal now. And to be honest, this chain works impressively well and saves us from a few if statements that would otherwise, at least in my honest opinion, make the code a little less readable due to the indentation of the blocks. Before we continue, we need another dependency. Let's quickly install the crate SHA-3, which allows us to hash the key we got in the same way we did through the browser before. And now we can work on hashing the API key we got. We first need a SHA-3 256 hasher, because that's the algorithm our key in the database is hashed with. Then we need to pass the API key from the HTTP headers to the hasher as bytes. After that, we can finalize the call, which hashes the API key with the SHA-3 256 algorithm, and leaves us with an output we can use to compare to the actual API key we expect and that we have previously fetched from the database. There's one thing we need to modify manually, however. The SHA-3 crate is largely generated, which leads to some issues with imports. This is why we manually need to add digits to the import from the SHA-3 crate. Only then our binary compiles correctly. With that manual import done, we can implement the comparison between the two keys. As we already have a string key with the one we fetched from the database, we need to compare it to a string version of the key we've just hashed. And we can accomplish that by using format and telling it to convert the hasher output to a lower hex string with :x. In our case, we first test whether both don't match, so it's worth adding another tracing and log statement outputting exactly that we received a call with a key, which was still wrong. After that, it's also worth adding another counter metric, which also increments the same counter we have already used at the beginning of this function when we tracked calls without any API key at all. That's still a nice indicator to find out when we get a disproportionate amount of unauthenticated calls from unknown sources, which by then is also a nice opportunity to think about implementing some form of rate limiting. At the end of our if statement, we can add a return statement with an error containing a tuple of an HTTP 401 unauthorized status code and once again a simple error message. Now there's only one last thing to implement in this middleware, and that is a return statement for the case that both keys match. And in that case, we return an OK and then use the next argument from the function to call the next layer in the chain with the request we got. We've created our middleware, which means that we can now work on integrating it. Let's jump back into our main.rs and navigate to the section where we define our Axum router. We only want to apply our auth middleware to very specific routes, which is what a route layer is exactly made for. It is only applied to all routes that come prior to it in the call chain, which in our case means that it is only applied to the create and statistics endpoint, but not for the redirect, for example. To integrate our middleware, we need a small helper that Axum provides. From fn and from fn with state, what we need in this case, are functions that basically create a layer from our function, such that we don't need to deal with any lower level layer semantics. From fn with state also allows us to pass our DB pool as state, which Axum then takes care of handling correctly and passing to each call of our middleware. Next, we need to take care of our patch endpoint for existing short links. This time, it's a little trickier because there are two handlers for different HTTP methods registered under the colon ID path. But gladly, a route layer is super flexible. What we can do is separate the handler registrations for patch and get, and then attach a route layer below the patch path. As this path is already nested, the layer is only applied to the patch path and only within the colon ID route. Even if we were to add another route above colon ID and below our first route layer, this one wouldn't apply to it. Wow, it's probably time again to test what we've created. So let's start our link shortener once again, in debug mode because some log messages always help, and then open a terminal where we can perform a few requests. If we, for example, try to access the statistics for a link without any API key header at all, we should correctly get back a 401 in return, which means that this part of our middleware works. And if we repeat the request but attach an API key header with the correct value, we should also get a successful response, giving us the statistics for one of our short links. If we now try to create a new short link without any API key, we should also be greeted with a 401, which shows that we've really attached the route layer correctly. And if we repeat the same request but attach an API key that time, there should be a successful response and a new short link created. Wow, we've got it. Let's appreciate that once again and remind ourselves what we've accomplished by now. That's a fully working link shortener that we could deploy anytime. There is, however, one very last thing left that we could do to make our creation even more perfect. Right now, when we create a link, we only try to persist it exactly one time, but our generated ID is still random. And this means that the more short links we save, the higher the chances of collisions become. Although we have an enormous amount of short links available for personal link shortener, we might still hit an already existing ID at some point. And in this case, we'll just get an error. We could now still call it a day and leave handling that to the client, or we do some last-minute work and fix that by implementing a retry for these cases, which gives us a little more room to breathe. And you know what? We should definitely spend that extra time to get it really right. So let's jump back into our routes.rs and navigate to our create link handler. To get what we want, we need to implement some form of loop that allows us to repeat the insert statement a few times if necessary. In this case, we can use a range that goes from 1 to 3 inclusive. That is what the equal sign in front of the 3 is for, which means that we get 3 attempts to store a new short link inside the database. Then we can pull the generation of our random ID into the loop. Each time the loop runs, we generate a new ID and hopefully get one we haven't had yet. We do, of course, also need to pull the whole sqlx query into the loop because the easiest method to find out whether we generated an ID we've already had is by trying to store our short link and see whether we get an error. Let's quickly reformat that code, but manually in this case, because Rust format seems to see no issue with this weird indentation. We, however, can see that and it just doesn't look right that way. Okay, we can now remove the last map error call from our usual and beloved map error chain, which leaves us with a result of either link or an sqlx error. Instead of that call, we place a match statement on new link, which allows us to handle the result ourselves, and a little more in detail this time. The first case to handle is a successful response with a short link, which means that we have successfully saved a new entity within our database. For that case, we can move our debug trace statement up into that block. This way, it basically runs in the same place as before. Then we can return from the function with a JSON representation of the newly created short link, which is what we previously did at the end of our function. The next case we need to handle is the error case. That is when some database operation simply failed. But instead of handling it generically, we can add another match statement, this time targeting the error returned, which allows us to handle two very specific cases of database errors. The first of those nested cases is an sqlx database error of kind unique violation. That's basically a unique constraint violation in database land, which means that we have, well, violated a unique constraint. And the only unique constraint we have for the links table is its primary key, which in the end means that we have generated a duplicate random ID. And in that case, we actually want to do nothing and just let the loop run again. The other nested case is basically everything else. If any other error than a unique constraint violation occurs, we do the same we did before. We take the error, map it to an HTTP status 500 response with our utility error mapper, and return that. Then we lastly need to handle the case that we have tried to persist a new short link 3 times, but still couldn't generate an ID we haven't already had. In that case, we can return an internal server error to the client with the usual tuple of an HTTP status code 500 and a simple error message. Although we are now technically done, let's do some really last work for observability. We can add an error trace in case that we exceed our retries to generate a unique ID, because if that happens too often, we have either chosen a really bad random generator or, which is more likely, have created so many short links that we are coming closer and closer to hitting the maximum number of available IDs we can generate. And lastly, we can also introduce a new metric, a counter in this case, that increments whenever we exceed our retries. This metric then allows us to create alerts that can notify us when this event begins to occur too frequently. We can then either increase our retries or think about increasing the number of available IDs. However, if this remains a personal link shortener, there are more than enough IDs available, and we should never hit this case. But if we ever do, we are now prepared. Wow, that's it. We've not only come to the end of this video, but we've also built a fully working link shortener ourselves. That's a pretty great accomplishment, so congratulations. But now this video is over, and if you enjoyed watching it and hopefully following along, leave a like and subscribe to this channel because it helps massively. And until then, see you in the next video.